recognition via human-like adaptation to speaker and language variety by University of Cambridge and University of Stanford. Please.
Great. Just the green button to go to the next slide. All right. Awesome. Well, thanks everyone for being here. I'm Nathan, and I'm here to present our work titled In Context Learning Boosts Speech Recognition via Human-like Adaptation to Speakers and Language Varieties. And I know it's a mouthful, and we'll get into that in just a second. But first, I'd like to thank my co-authors, Calbert, Yuka, Kim, Megan, and Dan at Stanford and Cambridge. They've been an immense help in this project. So we have kind of two big core findings in this project. The first is a rather straightforward one, that when we use in-context learning, which is essentially just providing examples to speech language models, we see improved performance. But we also find that in the process of providing in-context examples, we also see some human-like adaptation effects within the systems. So to give a little bit of background, as humans, we rely on a lot more than just the raw acoustic signal when we process speech. So as humans, we use the acoustics of our environment, the lexicosyntactic structure, what other words and sentences are within the utterance, what's the preceding context. This can be both linguistic, but also you can imagine there's other aspects to context, like a rapport with an interlocutor, or something that's happening in the real world, like a dog entered the room. We also use social information, things that we know about the interlocutor, either their linguistic abilities or something about the language that they speak. And finally, last but not least, we use information about the voice of that speaker. And this comes in many forms. So for example, we adapt to something about their vocal tract anatomy. We adapt to how quickly they talk or how slowly they talk, their speaking style, and of course, their accent, which we know from previous literature yields quite a bit of variation. At the same time, speech recognition systems need a lot of help. So for those eagle-eyed viewers in the audience, you might notice a gap between the performance of these speech language models on standardized varieties of English and all other English varieties, which represent the majority of the world's English speakers as non-native. So we performed a relatively straightforward experiment to see if in-context learning, that is providing examples at inference time, can facilitate speaker adaptation effects within spoken language models. So the model that we chose for this experiment was 5-4 multimodal instruct, which was the first, even though this is relatively recent work, the first model that we encountered that had an interleaved text audio space that allowed for the type of dynamic in-context learning we're doing. And we looked at 3 different corpora, L2 Arctic and CMU Arctic, which are kind of a pair of elicited speech data sets where people read identical utterances, and we have speakers, everyone speaking English, but from different language backgrounds. And finally, HEC, the Hispanic English corpus of native Spanish speakers who are living in the United States speaking English. So in a basic setup, to do ASR in a speech language model, we provide an audio file and a task prompt. In this case, the task prompt provided by the model makers was transcribe the audio into text. So it's a very simple prompt. However, when we want to do something like in-context learning, we have to provide transcribed examples. So this looks something like this, where we provide a task prompt, again, transcribe the audio into text, and then not only the audio file, but also the transcription, the ground truth transcription of that audio file. We prepend something like an initial prompt. This is, you're about to hear multiple audio files and then asked to transcribe the final audio file into text. And then because it's a spoken language model, we get to pass it through a dedicated audio encoder before everything is embedded in a shared text audio space and finally passed to a shared decoder where it autoregressively generates the transcription. So our first finding is this, that in-context learning improves automatic speech recognition without additional training, which is a really cool step, especially because we're already working with state-of-the-art models, and any improvements we make to state-of-the-art models make it that much more state-of-the-art. So we're seeing here on the y-axis is word error rate, so lower is better. And this is just our 0 to 3 shot word error rate performance in our model of choice, 5-4 multimodal instruct. And we see when we provide just a few more examples, going from 0 to 3 to 4 to 8, we get pretty robust improvements in word error rate, which also continues in the 9 to 12 setting, where we see a pretty significant difference between the average word error rate between 0 to 3 examples and 9 to 12 examples. But not everyone benefits equally. So what we're seeing here is a grouped bar chart, again, with word error rate on the y-axis, looking at the performance of the model without any examples versus with all 12 examples, which was just the number that we ran our for loop up to in our experiments. And we see across different varieties of English, there's drastically different performance gains, where some varieties, most notably L1 Mandarin, L2 English speakers, actually saw a decline in performance. And even though most varieties don't see a decline, there is quite wide variation, especially comparing it to L1 US English, where we see pretty robust performance gains in this already very powerful automatic speech recognition model. So you might ask, what explains these different gains? Is it something about the language or something about the corpus or maybe something else entirely? Well, what we're seeing here is the delta between the performance in 0-shot setting versus the performance in multi-shot setting. And when we color this just by the corpus that we're using, we see a pretty clear clustering effect where the corpora, the CMU Arctic corpus, which contains native English speakers reading read speech, we see the best performance gains. Our Hispanic English corpus, we see pretty modest gains. And then in our L2 Arctic corpus, which is non-native English speakers speaking English, we see the lowest performance gains. And again, there's Mandarin there at the end, where we actually see the model gets worse at transcribing Mandarin accented English audio. One explanation for this could just be language typology. There has been prior work that just shows systematically higher word error rates, for example, of tonal languages. We're not sure quite why this is, but it, to some degree, is a little disappointing to see that that we're making models better mostly for people that the models are already really good at transcribing. I think, at least from my perspective, the next finding is a little bit more interesting, which is just that the way that these spoken language models adapt to humans seems adapt to additional context examples seems to mirror something like we see with humans. So again, we have word error rate on the y-axis here that I'm going to show, and then the x-axis is number of shots, basically the number of contextual examples we're providing the system. And so this dark gray line is the average, and we see overall, if you squint a little bit, you can see a pretty clear diminishing return pattern where the more examples we give the system, the better it performs overall. When we compare this to parallel work, actually some of my other research looking at humans on the exact same data sets, we see something quite similar, where the first few examples provide a lot of improvement to the system, and that improvement seems to diminish quite rapidly. Another question you could ask is, can we further improve the accuracy just by telling the model to expect a non-native speaker? Again, because we have this multimodal embedding space, we can do things like telling the model to transcribe the audio clip from a non-native English speaker into text. And what we find is pretty interesting that across all varieties of English, even those of native English speakers, we see pretty significant improvements where just by telling the model to expect a non-native English speaker, even for native English speakers, the model seems to get better. And this is no in-context examples, even in our zero-shot setting, we still see this improvement, which I think is quite interesting. And maybe harks back to what we're talking about before, which is that humans seem to incorporate something about social information into their perception of speech. Yet another question you could ask, is our system really adapting to voices, or is it something about the task of in-context learning that's providing these gains? So what we're looking at here is the same versus different speaker condition, which means our in-context examples, are they coming from the same talker that our final audio transcription is coming from, or are they coming from a different talker? So we see with 1 to 3 examples, there's relative parity where our word error rates are pretty much the same when these first few examples are coming from the same talker as our final target audio file. When we expand to 4 to 6, we actually see pretty significant improvements in the same speaker condition and pretty negligible improvements in this different speaker condition. Again, so this is where all of the audio files in context are coming from different talkers than our final audio file that we're actually asking the system to transcribe. So you might expect this trend to continue, but actually it kind of flips back where we see again with 7 to 9 examples, there's relative parity before finally in our highest number of examples with 10 to 12, it actually inverses a little bit where more generalized examples in context seem to facilitate the best overall performance of the system. We're not sure why this is, but this parallels something like we know from human perception research, which is that the more variety you're exposed to, I guess I could say at inference time, though, as humans, I like to think we're doing more than inference, where we're having more generalized exposure does seem to facilitate this performance improvement. So to summarize, we see first that in-context learning improves speech recognition without additional training. So on average, across all of our data sets, across all of our corpora, we saw a 19.7% relative improvement in word error rates, where it seems like more audio files facilitates more improvement. We also see that these spoken language models exhibit human-like adaptation effects, both in these shared diminishing adaptation curves, where additional examples yield diminishing performance improvements. We also seem to be primed by expectations, just like these speech recognition systems. And we also seem to both benefit the most from more generalized exposure. And of course, our evidence, I think we need a lot more, especially because we're looking at one model. We're looking at a limited set of corpora that don't really fully represent the Englishes that are out there in the world. But it does seem to be interesting that maybe we could use these systems to help generate hypotheses about how human perception works, and maybe use these as tools for further research. Anyway, this QR code is broken, but I want to thank everyone for listening. Thank you.
Right. Thank you so much. Do we have questions from the audience? Please.